Welcome to Manasi Solutions. Today we are going to discuss about the topic Hausdorffspace in topology. So let's start. A topological space X2 is said to be Hausdorff space if and only if for any two distinct points A, B in X there exist two disjoint open sets, that is two open set U, V in tau such that U intersection V is equal to phi and A belongs to U, B belongs to V. If there exists such a pair of open set for any two distinct points in X, then we say that the topological space is Hausdorff. For example, consider the usual topology on R, and if A, B are two real numbers, distinct real numbers, and let the distance between A and B is equal to R, then consider the intervals A minus R by 2, A plus R by 2, B minus R by 2, B plus R by 2. These two are open sets and their intersection is phi, and A belongs to this open interval and B belongs to this open interval. So in R, for any two distinct points, we have such a pair of open sets, that is there exist two open sets that satisfies these conditions. Therefore R is what? R is Hausdorff space. Now consider a metric space XD and consider the topology tau generated by the metric space XD, and we know that every open set in this topology is the union of open balls which generated by this metric. And let A, B be two distinct points in X, and if the distance of A, B is equal to R, then consider the open balls B of A R by 2 and B of B R by 2. What are the open balls? Which is the set of all y belongs to X such that D of AY less than R by 2, and this open ball consists of all points X in X such that D of BX less than R by 2. So these two open balls are disjoint and these two are open sets in this topology, and A belongs to this open ball and B belongs to this open ball because these two are open balls centered at A and B respectively. So we have a pair of open sets that satisfies all these conditions. Therefore every metric space is a Hausdorff space. Every metric space is a Hausdorff space. Now consider the set X is equal to R union singleton set 0 1, where R is the real axis in R2. So this is a subset of R2. Now I'm considering a topology on this set, which is the set of all, which is the collection of all subsets of X which satisfies one condition. which contains all subsets of X which contains this point, which means if U belongs to tau, then U must contain the point A equal to 0, 1. So A is a member of every element in this topology. This is the topology I am considering on this set. Now, is this a Hausdorff space? This is the question. We know that a topological space is Hausdorff if for each pair of points AB, distinct points AB in X, there must exist two disjoint open sets such that A belongs to U and B belongs to V. So I am taking the first point A equal to 0, 1. Then for any point other than A, then for any point B in X other than A, there we can't find two disjoint open sets UV such that A belongs to U and B belongs to V, because whenever we consider an open set V which contains the second point B, that open set must contain A, because every open set in tau contains A. Therefore here the space is not Hausdorff, because whenever we consider an open set V from this topology, V contains A. There we can't find two disjoint open set U, V such that A belongs to U and B belongs to V. So the space is not Hausdorff. Now we are going to prove a result, a theorem from topology. This theorem states that, first statement is that the property of being a Hausdorff space is a topological and hereditary property. And second statement is that a sequence xn where n equal to 1 to infinity in a Hausdorff space cannot converge to more than one point. These are the two statements. And first statement states that when we consider in a Hausdorff space X and let Y be a topological space which is homeomorphic to this space, then Y is also Hausdorff. This is topological property. A property is called a topological property if the property shares from a space to all other spaces which are topologically equivalent to the first space. So here Hausdorff's property is a Hausdorff's property is a topological property, because if a space X is Hausdorff space, then every topological space which are topologically equivalent to X is also Hausdorff space. Here we need to prove this, and we say a property P is hereditary if a topological space X is a set space, a property P, and it shares this property to all its subspaces. That is, if Y is a subspace of X, then Y is also set space the property P. Such properties are called as hereditary property. So here Hausdorff's property is a hereditary property because if X is a Hausdorff space, then every subspace of X is also Hausdorff. Here we need to prove these two things. So first let's prove the property of being Hausdorff is a topological property. For that, consider a Hausdorff space X and let Y be a topological space such that Y is topologically equivalent to, that is, Y is homeomorphic to X, and let f from X to Y be the homeomorphism. Then we know that a homeomorphism is a bijective function for which the function and its inverse is continuous. So here f is bijective, f is continuous, and f inverse is also continuous. We need to prove that Y is Hausdorff space. Therefore, consider two points A, B in Y. Then f inverse of A and f inverse of B are two points in X. Since X is Hausdorff, there exist two disjoint open sets. That is, there exist two open sets U, V such that U intersection V is equal to phi and f inverse of A belongs to U and f inverse of B belongs to V. And this implies that A belongs to f of U and B belongs to f of V. Since f and f inverse are continuous and f is bijective, we can say that f of U and f of V are open in the topological space Y, and this open sets contains A and B respectively, and U intersection V equal to phi implies that f of U intersection f of V is equal to phi. Therefore, here f of U and f of V are two disjoint open sets in Y which contains the points A and B respectively. So for any two points A, B in Y, we can find such a pair of open sets. Therefore, Y is Hausdorff space. So we can say that if a space X is Hausdorff, then every space Y which is topologically equivalent to X is also what? Hausdorff space. Okay. Next we need to prove that the property of being Hausdorff is a hereditary property. For that, consider a topological space X which is Hausdorff, that is a Hausdorff space X, and let Y be A or A. I am taking A. Let A be a subspace of X. We need to prove A is Hausdorff. For that, let A, B be two distinct points in A. Here A is a subset of X. Therefore, these 2 points belongs to X, and X is a Hausdorff space. Therefore, we can find two open sets U, V. Two open sets. We can find two open sets U, V in X such that U intersection V is equal to 5 and A belongs to U and B belongs to V. We know that if O is open in X, then O intersection A is open in A. So here U and V are open in X, so this implies U intersection A and V intersection A are open in A. Also, U intersection V equal to 5 implies that U intersection A intersection V intersection A equal to 5. So if U dash is equal to U intersection A and V dash is equal to V intersection A, then this implies that U dash and V dash are two disjoint open sets in A such that A belongs to U and A belongs to A implies A belongs to U intersection A and U intersection A is equal to U dash. Therefore, A belongs to U dash, and similarly we can say that B belongs to B dash. So whenever we consider two distinct points A, B in A, there exist two disjoint points, disjoint open sets U dash, V dash in A such that A belongs to U dash and B belongs to V dash. This implies the subspace A is Hausdorff. So if a topological space is a Hausdorff space, then every subspace of that space is also Hausdorff. Okay. And next we need to prove that whenever we consider a sequence x1 in a Hausdorff space X, then this sequence does not converges to more than one point. If a sequence is not convergent, there is nothing to prove about it. So suppose the sequence converges to 2 points. First we suppose that the sequence converges to more than one point, and at last we will prove that two limits are equal. Okay, then suppose the sequence xn equal to 1 to infinity be a sequence in a Hausdorff space X, and let the sequence converges to two distinct limits A, B in X. At last we will prove that A equal to B. Now AB belongs to X implies that here X is a Hausdorff space, so A and B are two distinct points in X. So this implies that there exist two open sets U, V in X, two open sets U, V in X such that U intersection V equal to 5 and A belongs to U, B belongs to V. And we say that a sequence xn converges to a point x if for each open set O containing x there exists a natural number n such that xn belongs to O for all n greater than or equal to n. So here A is a limit of the sequence xn, and U is an open set containing A. Therefore, there exists a natural number n1 corresponding to this open set U such that xn belongs to U for all n greater than or equal to n1. And similarly, B is a limit of the sequence xn, and V is an open set containing B. Therefore, there exists a natural number n2 corresponding to this open set V such that xn belongs to V for all n greater than or equal to n2. Let n be the maximum of these two natural numbers n1 and 2. So n greater than or equal to n1 and n2. This implies for all n greater than or equal to n, sequence xn lies in both U and V. So this implies xn belongs to U and xn belongs to V for all n greater than or equal to n. And this implies U intersection V is non-empty. But by our hypothesis, U intersection V is an empty set. This is a contradiction. Therefore, the two limits A and B must be equal. Therefore, A equal to B. Okay. Next, we are going to define embedding. So, consider two topological spaces X and Y, and if X is homeomorphic to a subspace A of a space Y, then we say that X is embedded in Y. If X is homeomorphic to a subspace A of Y, then we say that X is embedded in Y, and that homeomorphism is called as embedding, and the homeomorphism F from X to A is called as embedding of X in Y. Embedding of X in Y. So, a topological space X is embedded in Y if the topological space X is homeomorphic to a subspace A of the space Y, and the homeomorphism is called as embedding of X in Y. So, let's go to some problems. Consider R with the usual topology, and let A equal to closed 0, 1. and here I am considering subspace topology on A by R, and consider the open interval 1 by 2, 2, which is open in R. Therefore, by the definition of subspace topology, 1 by 2, 2 intersection A is open in A, and this is what 1 by 2, 2 intersection the closed interval 0, 1, and this is the interval 1 by 2, 1. So here the interval 1 by 2 closed 1 is open in the subspace topology A, but it is not open in the whole topological space R. So a set which is open in A subspace topology need not be open in the whole topological space. And similarly consider the set A equal to open 0, 1, and consider A as a subspace of R. Then 0, 1 by 2 is a closed set in the whole topological space R. So by the definition of closed set in a relative topology or subspace topology, 0, 1 by 2, the closed interval 0, 1 by 2 intersection A is closed in A, and this set is intersection open 0, 1. This is open 0 closed 1 by 2, and this set by definition this is closed in the relative topology A, but this is not closed in R. So by this example we can say that a set which is closed in a subspace topology need not be closed in the whole topological space X. And one more problem. Suppose f from x to y is a continuous function A, and A is a subspace of x, then the function f restricted to A from A to y is also continuous. F from x to y is continuous, so this implies that f inverse of u is, this is possible if and only if f inverse of u is open in x for every open set u in y. Now consider f restricted to A inverse of u, and this is equal to the set of all x belongs to A such that f of x belongs to a of x belongs to u, and this is equal to the set of all x belongs to A such that for every x in A, f restricted to A of x is equal to f of x. So we can write f of x belongs to u, and this is the set of all x belongs to x such that f of x belongs to u intersection A. So and this set is f inverse of u intersection A. Whenever U is open in Y, and since F is continuous, F inverse of U is open in X, and this implies F inverse of U is F inverse of U intersection A is open in what? In A, and this set is F restricted to A inverse of U, and which is open in A. So we can say that whenever U is open in Y, then F restricted to A inverse of U is open in A. Therefore, the function F restricted to A is continuous. Okay, bye.